Alright, so we're back in Houdini, and as you can see the UI looks a bit different now, and that's because I've scaled it up a bit, and you can adjust the UI size if you go to Preferences and User Interface. So I've just scaled up the global UI. You might have the play bar set to normal, but I like to keep it compact because it just saves a bit of screen space. And then you can also set your default desktop here as well. And there's tons of other settings and presets that you can set here. So the first thing you might want to do when you create a new project is to go to File. And then if you click New Project, you'll get this pop-up window. And here you can name your project. We can say Houdini Tutorial. And then you can pick your product path. So we can just set it to the desktop for now. So this will create a folder on my desktop called Houdini Projects. It will also set this environment variable called $job. And what $job environment variable is essentially just a shortcut to a path on your disk. Then below here, you have some project folders. So these are going to be sort of preset folders. You can also set custom folders. I actually never create new projects this way, but it's good to know that this is an option. And I think the benefit is that it sets the $job for you, so you don't have to set it manually. You can set it manually as well if you go to File and Set Project, and then you can pick a folder where you want your $job location to be at. But for this tutorial, I'm going to do it through the new project window. But I don't need all of these folders, so I'm just going to uncheck all of these. I might say render. I don't need Alembic, I think. I don't need simulation. We'll keep these 3 folders. Accept. And then I think I actually need to save this HIP as well. Control-Shift-S to hit save. And then we can click on this $job here, which takes us to that folder. And then we can just save the HIP file here. So in 99.9% of the cases when I start a new scene, I'll usually start by creating a geometry node. And this one, I'll usually name something like build_scene. And if I hit the C key, we get this color palette. And here we can change the color of our nodes. So I'm going to pick the purple color. And there's a good reason why I named this in all caps. And that's because in Houdini, any node that have uppercase letters will automatically get pushed to the top of any list. So if I hit Shift-W to bring up the tree view, you can see that we have our node here. And then I can create another geometry node. But if I rename my other geo node to uppercase and change this one to lowercase, you can see that they swap places. And this is also dependent on the alphabetical order. So if I name this A, you can see that now it gets moved to the top again. I'll delete this one and then I'm just gonna rename this again, like that. And from here, we can either double click or we can hit the letter I to jump in or U to jump up. So I for in, U for up. Okay, so now when we're on the geometry level, we're going to create a simple Mograph setup. And usually in Cinema, a lot of times what you'll do is you'll create a cloner and then you'll clone some objects onto it. And then you'll control those clones with effectors and falloffs and all that stuff. And the closest equivalent to the cloner in Houdini is the copy swap. And it comes in a couple of different flavors. But the one we're going to use is the copied points, and that's also the one that I use most of the time. This node has 2 inputs, and the first one is going to be where you plug in the geometry that you want to instance or copy over. And then the second one is going to be the target points or the target coordinates that you want to copy to. So for example, we can create a sphere, plug it into the left, and then we can create a box and plug it into the right. And now you can see that we copy a sphere onto every point of this cube. It's pretty simple, right? So essentially what we've just done is we've just mimicked the behavior of changing the mode of the cloner to object mode and then referencing an object, a cube in this instance, that we're then able to copy over to each vertex or point. Which brings me to a good point. And if you watched the last video, you'll know this already, but if you didn't, here's a quick rundown. So Cinema doesn't make the distinction between a point and a vertex, but Houdini does. Points in Houdini are essentially just coordinates in space, so that's pretty easy too. That's kind of what we think of when we think of vertices. But in Houdini, a vertex describes a polygon's connection to that point. So you can almost think of vertices as being the corners of a polygon. And if we take a look at the box, for example, and hit this I button, we can see that we have 8 points and 6 primitives. And each primitive in this case have 4 corners per primitive. So 4 times 6 equals 24. And each of these corners can have different information stored on them. So they could have different UVs, different normals, etc. Most of the times, you're probably going to be working on the point level and the primitive level either way. But for now, just know that Houdini does make that distinction between a point and a vertex. All right, moving on. So from here, we're going to create a file swap, and this node is what we can use to bring in external files into Houdini. So I'm gonna open up our $jobs folder here. We can pick this Houdini logo. Houdini natively supports Adobe Illustrator files, but they need to be saved out as Illustrator 8, I believe. So it's kind of similar in the way it works in Cinema. So we can hit accept, and now we don't see it because it's off-centered. But if I hit space H, it will center around this object. And you can see that it's off-center. So we can use a super handy node called match size. And this will automatically snap it back to the origin. And if we middle mouse click and hold, we can see that it currently consists of Bezier curves, but that's fine. I will drop down a attribute delete though. And then we'll remove the CD attribute because we don't want color. Like that. And then we can drop down a poly extrude to give some volume. And you can see now if I middle mouse click the poly extrude, now it converted it to polygons. I can then extrude it out. And then we also want to output the backspace. So we got something like this. I'll also want to drop down a new match node just to make sure that it's always in the center. So what I'll want to do now is to fill this object with some points, and then we're going to copy over these spheres onto those points. So one way we can do this is by converting this into a volume with the ISO offset. And then we can crank up the uniform sampling here to 50. And then we can scatter some points inside of this volume with the scatter stop. So now we have a lot of points. I'm going to reduce the point amount to like 100 maybe. And then we can plug this into the copy point nodes instead. And now the spheres are way too big. So we can either scale down the sphere itself, or we can apply an attribute that will scale down the spheres for us. So then you might be wondering, what is an attribute? An attribute is just a named piece of data attached to your geometry. So it could be a number, it could be a vector, it could be a string, a matrix, anything. If you think about the last time you used a Mograph cloner, for example, you might drop down a bunch of objects and then maybe you'll use a random effector to vary their scale or color. In Houdini, the scale and the color would be two attributes. But in Cinema, those color and scale values live on the cloner itself, so you can't easily grab it, pass it somewhere else, or use it to drive a totally different effect downstream. Of course, you can always hack it together with Espresso or using maybe the inheritance effector, but in Houdini, that information is available to you at any stage. So you can read and store values in an attribute, reference it later, and so on and so forth. One thing that's good to know is that Houdini has a bunch of built-in attributes that the software and renderers already know how to read. Here are some of the most common ones that can be worth to memorize. We'll touch on some of them in this video, but the one we want to use at this moment is at pscale in order to control the uniform scale of our instances for every point. So in order to create this attribute, we can drop down a attribute create node. And here we can name the attribute, and we'll want to name this pscale. And this is going to be on our point level, and it's going to be a float value, so it's going to have decimals. And here we can set the value to 0.1. So now if we check our geometry spreadsheet, you can see that we have a pscale attribute of 0.1 for all of the points. And we can modify this, and you can see that it updates both in the viewport, but also in the geometry spreadsheet. So that's an easy way to set a uniform pscale for all the points, but we can also vary this per point with a attribute randomize. And by default, it will just add random colors, but we want to affect pscale. And right now it's overriding this initial pscale that was set. So we can set it to multiply, and now it will just use that initial value and multiply it by that. So I'll change the values here, something like this perhaps. And then for good measure, I'm just going to change this back to 1 because it's not a vector, it's a float. And in this case, I also want way more points. So I just upped the force total count, and then I scale down the points a bit further. I'm also going to add some UVs for our spheres. So we can use the UV project node and then change the projection to polar. And then I'll add some normals. We can also modify attributes with code by writing Vex in Wrangles. Vex is a C-like programming language that allows you to directly access, create, and modify a lot of different components inside of Houdini. In this case, we're modifying geometry. So for example, we can set be at CD, which stands for color, and then we can do something random based on the current point number, and that will give you random colors. And you can also write Vex code visually with VOPs. And the closest equivalent would be something like Espresso in Cinema 4D. So if we hop in here, by default, we get access to some of these most commonly used attributes that you might need. And then you can write them out as well. So we can drop down a random VOP. And then let's create a random value based on the point number. So each point gets a random value. And then we can remap this with a ramp parameter. And if we plug it into CD and jump up one level, we can see that now we have this parameter window that we can remap our colors with. So let's pick the black to orange maybe. So as you can see, there's multiple ways to access and write and modify attributes in Houdini. So now we have some spheres cloned onto our points, but if we middle mouse click here, we can see that we have a lot of geometry. So it would be better to instance this, just like we can do in Cinema 4D. And the way we can do that is by clicking this button here on the copy to points top, which says pack an instance. And now you can see that we changed the geometry count from, well, over 1 million points to just 5,000 points. And of course, a Mograph setup wouldn't be complete without a Falloff. So we're going to create a super simple Falloff here. So right after the points, we're gonna make some space here. I'm gonna drop down another sphere. But I'm going to keep the sphere as a primitive and not a polygon mesh. And this essentially is just an instance of a sphere. So it's just 1 point. And then we can drop down a attribute transfer. And then from this, let's create a Falloff attribute that we can transfer over. So we'll need 2 attribute creates, one on the points, and we can call this Falloff. And this should be set to 0. And then we can copy this node over to the sphere and change the value to 1. So now the sphere will have a Falloff value of 1, and the points will have a Falloff value of 0. And then with the attribute transfer, we can transfer over this value to our points. And in order to visualize this, we can hit this I button, and then we can toggle this Falloff attribute here. So now it's all red, but if we go to the attribute transfer and uncheck everything except for the Falloff attribute, so the Falloff attribute is the only attribute that we want to transfer. And then we can lower the kernel radius and we can lower the distance threshold. And as I do this, we can see where our Falloff is affecting our points. And if you want to, you can also blend this so that you get a bit more of a spread. And then we can animate the sphere. I could either animate it on the actual sphere node itself, but I'm going to create a transform node. And then with the transform node, we'll set it to -1 maybe. And then in order to set keyframes in Houdini, you do that by holding the Alt or Option button and left click. And that will create this green box indicating that we have set a keyframe, and we can also see that in our playbar down here. And then let's go to maybe frame 48 and set it to 1. And then we can hold Alt again and left click, and now we have 2 keyframes. And if you want to see the easing of those keyframes, we can hit Shift left click, which brings up the animation editor. And this is pretty similar to how it works in Cinema. I'll just add a little bit of easing to this. Pretty standard. And now we can close it. Now we can play back. And if we take a look at our points, we can see that the Falloff animates through the points. I'm going to increase the distance a little bit and increase the blend width. Maybe not that much. I'll just adjust where it starts and where it ends. Cool. So we have the Falloff. And then let's modify our pscale based on this Falloff. And this attribute will ripple through all the nodes below it. So if we toggle our spheres, and we can modify this pscale value with a attribute adjust float. So the attribute name that we want to modify is already set to pscale, so that's great. So we can set it to multiply, and then we can change it from constant to float attribute. And then here we can pick our Falloff. So now, as this animates through, you can see that we're revealing those spheres. So what we've done is essentially recreate a spherical Falloff. So now when we have this, I'm going to create a null. And I'm going to call this null out in caps and then geo. So now when we get to this stage, it might be nice to have some different objects that we can instance onto our points. Because now we only have spheres, but what if we want to have some variation? So we can create a box, for example. Here I'm going to add some UVs. We can change the spacing to 0. And then I'm going to add a poly bevel. And then we can drag the distance up. If I hit Shift W, we can enter shaded wireframe mode so that we see these lines. And then I'm going to up the division size to 4. just to make it a bit more round. I'll set the distance to 0.0.5, and then we can subdivide this. And lastly, I'm gonna add some normals. I'll set the weighting mode to by face area, and then we can create a null. Just call it out_box for organization. And by the way, as you're building your node tree, you might end up having something that feels a bit disorganized like this, for example. So if you want to straighten it up, you can select all the nodes that you want to straighten. And then if you hold down the A key and then left click and drag down, they'll snap together vertically. And if you hold down A and left click and swipe left or right, they'll then conform horizontally. So that's a pretty satisfying move to do. I'll copy this subdivide node and just put it on the sphere as well so that we get some more subdivision. And then I'm going to copy this null, name it out_sphere. So we have 2 objects now, and maybe we want to have 3 objects for good measure. So I'm going to copy this box section, and then I'll delete the box, and then we're going to create a platonic solid, which gives us a pyramid. I'll rename this to out_pyramid. Now when we have these 3 objects, we can merge them. And then I'm going to drop down a new node called connectivity. I'm going to change the connectivity type from point to primitive so that we get a attribute on our primitive level. And what the connectivity sub does is that it creates a unique number or value for each set of connected primitives or points. In this case, we've set the connectivity type to primitives, so it'll add that attribute to the primitives. So in this case, the box is going to have the number 0 because the merge node takes inputs from left to right by default. And then the sphere is going to have a number 1, and then the pyramid is going to have number 2. So I can plug this into our copy to point sop. And now you see that we're just copying over every object on every point, and that's not really what we want. So we need to tell the copy to point sop which instance to use. And the way we can do this is by adding a number on our template points that corresponds to the number that this class attribute is set to on our instances. You can obviously do this manually with like a wrangle or a point vop, but there's a handy node called attribute from pieces that does this for us. So on the left, we're going to plug in our template points, and on the right side, we need to pipe it the geometry that we're looking to instance. So I'm going to take this connectivity sop and pipe it into the right here. I won't go through all of the settings that this node has to offer, but the important bits is that we need to change this piece attribute from name to class, since that's what our attribute is called. And then in this case, I'm going to change the mode from cycle to random. And if we go to our point level here, we can see that now we have a class point attribute, and it automatically fetches the maximum value from the connectivity sop. So it won't go over 2 in this case. And then there's one last bit we need to do. We need to go to our copy to point sop, and then we need to check this piece attribute, and we need to change this from name to class as well. And now you can see that we get a unique instance per point. So now it distributes it uniformly, but we can change the weight method from uniform distribution to piece weights. And then if we click the autofill pieces, it'll automatically fill in those values for us. So now, for example, I can say that I only want 20% boxes. Maybe we want to have the full weight of the spheres, and then we can set 0.3 to our pyramids. So now when I'm looking at this, we can see that we have a lot of intersections. So maybe we can figure out a way to de-intersect these. And the way we're going to do this is with some simulation. And the strategy here is that we're going to convert our high-res geometry to something low-res and simple to simulate. And then we're going to use that simulation as a guide to animate our high-res set of geometry. As a matter of fact, I'm just going to up the subdivisions. And then I'm just going to swap the places on the normal. So the first thing I'm going to do is I'm going to copy over this copy to points. And we can name this copy to points HQ. And then we can name this copy to points LQ for low res or low quality. And now we're starting to get some crossing wires. So here's a way to clean this up a little bit. I'm going to drop down a new null, and then I'm going to call this in instances. And then from here, I can drop down a object merge. And if we drag this null into the object merge, we essentially have created a link between this null and this node. So now I can just replace these. So at least we have one less wire crossing. I'm going to copy this object merge once again. And in this stream, I'm going to want to poly reduce these objects so that they don't have as many primitives. And there's a node for this, and it's conveniently called poly reduce. And we can change the percentage to 1. So now we have a lot fewer polygons. So we started at like 8,000 or 8,000. And now we're at 80. And this will help with the simulation times for the rigid body solver. The way we can create simulation in Houdini is by working inside of a new network that we haven't touched upon yet called a DOPnet. There is a SOP level rigid body solver that comes with a lot of different bells and whistles, but in this case I'm going to show you how to set it up manually so that you can get an idea for what DOPS looks like and how it functions. So I'm going to create a DOPnet, and then we can pipe our geometry into our DOPnet. And if I double click and jump in, we can see that we changed from geometry to dynamics. And this is where we'll set up our simulation. Now, I'll admit, DOPS is a pretty difficult topic to cover, but here are the bits and pieces that you need to know to get started. In SOPs, operations flow top to bottom, but in DOPS, operations flow left to right, top to bottom. That's the first thing to keep in mind. And then, in general, you're going to need 3 components to make simulations. The first one is going to be your solver, and there's a multitude of solvers here, and the one we're going to use is the rigid body solver. And these solvers, more often than not, need an object that is going to hold the geometry that we're going to simulate. So in this case, we're going to use a RBD packed object because we have packed instances. And then we're going to want to change the geometry source from SOP to first context geometry. And what that means is that we're fetching the first input of this DOPnet. Make sense? So we have first context geometry. You can pick the second context geometry if you want, but that is what this means essentially. You can also pick a custom SOP. So if you click this button, you'll be able to grab a null or something. But since we've already wired in, I'm just going to keep it to first context geometry. And then the third component that you probably will need is some forces. So there's a multitude of forces here as well. Now currently, if we scrub through, we can't see anything. And that is because we have some animation where our instances scale up and scale down. And by default, the DOPnet will only fetch the first frame that it finds. So here's what we're going to do. I'm going to take this Falloff that we created earlier and branch it off into a different area. And then I'm going to disable this multiplication that we did with the Falloff so that we have an initial state that we can start simulating from. So now if we hop into DOPS, we can see that we have some objects. If I hit play now, nothing happens because we don't have any forces. But we're going to use this Falloff that we created to control the pscale or the scaling of these instances on simulation time. So I can create a null here and call it out Falloff. And then from here, we're going to hop back into our DOPnet. And now we're going to bring in that Falloff into our simulation. So you have 2 inputs here on this solver. So you have the pre-solve, which will calculate before the simulation happens. And then you have post-solve, which will calculate after the simulation step happens. So we're going to use the post-solve input, and I'm going to create a pop wrangle. And I know this is code, it's scary, but it's going to be super simple, I promise. So first we're going to create a variable, and this variable is going to hold that Falloff from SOPs. So we can type float, because it's going to be a float variable, and we're going to call it Falloff, and this will equal to a function. And then we're going to fetch this point attribute. And we can do this with a function point, and this needs some arguments. If we click on this function and hit F1, we'll get this documentation that describes the arguments or the values that we need to enter in. So first it needs the geometry. So that's going to be the geometry stream. So let's set that up. So in here, I'm going to set the input to be 1, and we're going to set up the inputs in this input tab here. And confusingly enough, input number 1 is in code described as 0 because computers work that way, I guess. So what we're actually saying here is that we want to get input number 2. So 0 is input number 1 and 1 is input number 2. And then up it goes. So input number 1 is going to be the simulation geometry itself. And then input number 2, we're going to fetch that null that we created, the Falloff null. So I can click this button here, and if we scroll up, we have out_Falloff here. We can hit accept. And now we're fetching this null into DOPS essentially with this pop wrangle. Okay, so we have that. What we then need to specify is the attribute name. And the attribute name is Falloff. And you can see here that it asks for a string. And the way you define strings in Vex is by using these quotation marks. You might see people using single quotation marks as well. Both kind of works. So I'm going to type in Falloff. And then we need to specify the point number. And we can easily get this by using the @ptnum attribute. And this is a standard Houdini attribute that gets calculated anytime you create any type of geometry. And then we need to add a semicolon to close off the line. And lastly, we need to set this value on an attribute in DOPs. And this is going to be the same attribute that we set in SOPs. So we're going to type F for float and @pscale. And then we're going to remap this. And there's a function for this as well called fit. And this is similar to change range in Redshift, for example, just in code. And there's a couple of different flavors of this function. But since we know that the falloff is a value between 0 and 1, we can use this version of this function, fit01. So we're going to remap our falloff between a small value and 1. And then we need to close this off as well. And the reason why I don't set this to 0 is because if we do, the rigid body solver will freak out. So now if I hit play, we can see that they disappear, and then they scale up, and then they disappear again. This actually used to be super complicated to do, but since Houdini 19, the rigid body solver reads and sets or updates the pscale value automatically. Just a little disclaimer, as I was watching through this tutorial before posting, I realized that I missed one thing. So by default, Bullet won't recalculate the collision geometry when scaling objects. So what you can do to fix this if you want to is to switch the popper angle from post-solve to pre-solve. And then in order to fix this, we just need to reset the ID. So we can do this by typing i@id equals to -1 and then close that off. So now if we resim, it will be a little bit slower because it has to recalculate the collision geometry on each frame, but we'll get accurate collisions this way. Also, you can just leave the input number 1 to none. There's no reason to set it to myself in this instance. Apologies for that. Back to the tutorial. So now when we have this, we can add some forces. And there are a multitude of forces, but we can add a gravity force, for example. Pipe it in there. So this will get calculated first, and then the gravity will kick in. But since we're working with packed geometry, we could also add a pop force, which is a particle force. And that is because packed geometry is essentially just points in space, just like particles. So you could do this and set your force or gravity here, but we can just leave the normal gravity DOP. However, when we play now, we can see that the objects just fall. So it would be cool to have something similar to follow position or follow rotation that we have in Cinema. And we can set this up with constraints. Before we do that though, I'm just going to go into my RBD packed object, and then I'm going to click on this bullet data here. So right now we're displaying the actual geometry, but we can also display the guide geometry or like the collision geometry. We can see here that it's set to convex hull, and that's usually the geometry representation that Bullet likes, or at least that's one of the fastest ones. If you do only have like boxes or spheres, you can set it to that, and that will be even faster. But in this case, since we have a pyramid and stuff, convex hull is the way to go. I will scroll down to collision padding though, and scale this down a little bit. So now we get a more accurate depiction of our collisions. And one thing that tripped me up in the beginning was that all of a sudden my geometry just stopped simulating. And that might be because this enable sleeping is turned on. And what this does is if the motion is below a certain threshold defined here for a certain amount of time, which is defined in the sleeping time here on the solver, the geometry will essentially deactivate, so they won't be able to move. So most of the time I tend to just uncheck this. But it can significantly speed up your simulations if you have millions of objects. Another handy quick tip while we're on the subject of rigid body simulations is that you can see now on the first frame we have some intersections. So if you go up one level and if you create an attribute, and this attribute has to be an integer, which means that it's whole numbers. And if we name this attribute found overlap, set the value to 1. So if I hop down into DOPs again and bypass this popper angle, and the other thing you're going to want to do is to go to the RBD packed object node and click solve on creation frame. And this will make the bullet solver de-intersect on the first frame. So that's a pretty handy attribute that the bullet solver understands. All right, so let's set up some constraints. And constraints in Houdini is essentially just lines with attributes. So if I search for constraint and go to RBD pin constraint, it'll drop down these two nodes and we can wire these in. So in this case, since we're doing our high-risk geometry over here, I'm not even going to bother piping it into the first input. So we can use this proxy geometry input instead. This is designed to work with the SOP level RBD solver, but we can still use the constraints so we don't have to set up the attributes manually. So I'm going to pipe the third output to the first input of the DOPnet. In the RBD pin constraint node, we have a lot of different options here and settings, but the only thing I'm going to do is switch the pin type from hard to soft. And then in the RBD constraint properties, I'm going to lower the stiffness to, let's say 5. And I'm going to up the damping to 5 as well. And I'm also going to pipe our constraints, which is the middle stream here, and put that into input number 2 of the DOPnet. And we can take a look at the stream, and all it is just small lines with attributes on them. So now if I hop back down into DOPs, we're going to set up a constraint network. So we can type constraint network, and this we're going to pipe in after the RBD packed object, but you could pipe this in after the RBD body solver as well. Then we need to specify the constraint type, and the node we're looking for here is the bullet soft constraint relationship, like so. And then we need to change the geometry source from SOP to the second context geometry, since we're piping the constraints into the second input here. I think that's it. I'm going to load the stiffness in here to 1 though, because we're going to control the stiffness in SOPs. And I think that's all we need to set up. I'm going to go back to my RBD packed object and just uncheck the show guide geometry and display the simulation geometry instead. So now if we hit play, we can see that now they don't fall down and they kind of stick to their original position. Lastly, I'm going to enable my popper angle again, and then we're going to jump up 1 level. And what we want to do now is to transform the high resolution geometry based on our low resolution dynamic simulation. There are multiple ways of doing this, but the easiest way that I found is to just create a DOP import. I'm going to drag the DOPnet in here. I'm going to remove the asterisks, and then I'm going to click this RBD packed object to grab that object. So now we have this. But instead of fetching geometry, I'm going to create points to represent objects. So now we just have points that are essentially representing that simulation data. What we then can do is create a transform pieces up. We're piping the high-res geometry onto the left, and then we'll just put the template points or the simulation points into the middle section here. So now if I hit reset on the simulation first, and if I toggle the out null and hit play, we can see that we have our high-res geometry animated by our simulation, and it's pretty fast. And you might also want to copy over the velocity in order to get somewhat accurate motion blur. And now when we have this, we might want to create like a preview, playblast, or flipbook is what it's called in Houdini. So if we go to this icon and hold down and click the flipbook with new settings, I'm going to change the end frame to be 1048, so we have 2 seconds, and then I'm going to go over to size and just make sure that this box here is unchecked so that we get the current resolution that we're looking at. All right, so let's recap. We started off by recreating Cinema 4D's cloner using the copy to points op. We also took a look at how we can instance geometry and how we can art direct the distribution of those instances across a number of points. From there, we've also learned how to import external vector files using the files op, and we also explored one of the most fundamental concepts in Houdini, attributes. I hope now that you've come to realize that most of the stuff in Houdini is essentially just points in space with bits of information attached to them, and that those attributes are what allows us to control operations inside of Houdini with precision and detail. At the end, we also set up a low-res simulation using the rigid body solver that we then used as a guide to transform the higher-res version of our instances. In the next part, I'm going to show you how we can light and render this. I'll also show you how to set up cameras, go through some basic render settings. Most of it should be pretty familiar because we're going to use Redshift, so all of the render settings and stuff will be mostly the same as it is in Cinema 4D. Thank you so much for watching, like and subscribe for more, and I'll see you in the next one.